Hello everyone, this is Shweta and welcome to VLSI Point. So in this course, I am going to cover all the Verilog topics from basic level to advanced level in very simple words. So if you are a beginner and you are just planning to learn Verilog, you just want to build your concept, then you must join this course. Even if you have some basic idea about Verilog, but still you are not confident with some advanced topics, then you should also join this course. So in this lecture, we will learn about HDLs. What is HDL? What are the advantages and why we should use HDL? We'll learn everything in this lecture. So without any delay, let's get started. So HDL stands for Hardware Descriptive Language. It is a specialized computer language which is used to describe the structure and behavior of electronic circuit. Whenever we are talking about HDLs, so directly or indirectly we are talking about a piece of hardware. So this language is related with hardware circuits. In early 70s, when we didn't have HDLs, at that time pen, paper and drafting tables were used to describe the specification of the circuit. Since now we have HDLs, so we can simply translate our ideas to the digital circuit. HDLs include the notion of time and it also supports concurrency. So this is the property of HDL. Whenever we are talking about notion of time, so it is basically related with the time delays of digital circuit. In real time, each and every hardware circuit have some time delay and HDLs include that time delay. So this is the property of HDL. Talking about another property which is concurrency. So concurrency is nothing but whenever two things are happening simultaneously, that is called concurrency. Suppose in a circuit there are two blocks and both the blocks are executing at the same time. So this is the example of concurrency and HDLs also support the concurrency. So it is a concurrent language. However, if we are talking about other programming languages like C and C++, so these are not concurrent languages. These are sequential in nature. So this is all about HDLs. Verilog and VHDL, both are hardware descriptive language. So we'll start with Verilog. So Verilog is a hardware description language and the current standard is IEEE 2001. Verilog is basically used to describe the low-level hardware. Actually, Verilog is a very flexible language. In Verilog, there are some predefined basic gates and digital circuits which are already saved in digital library of the Verilog. So we can directly use those blocks and that are known as primitives. Verilog is a very much similar to C language whenever we are talking about syntax, but still there are some difference between Verilog and C language. So let's see what are the difference. Verilog is a hardware description language which is used to model electronic system. However, C is a general purpose programming language which allows the structured programming. HDLs have notion of time. However, C language don't have the notion of time. Verilog helps to design and describe the digital system. However, C helps to build operating system and database compilers, interpreters. In case of Verilog, the file extension is .v. In case of C language, the file extension is .c. So these are some basic difference between Verilog and C language. Now we are moving towards VHDL. So VHDL stands for VHSIC. That means Very High Speed Integrated Circuit Hardware Description Language. VHDL are basically used to model behavior and structure of digital system at multiple abstraction levels. VHDL is a kind of strongly typed language and it is very deterministic. VHDL is an old language and it has developed in 1980s. VHDL syntax is non-C type, and the advantage of VHDL is that we can easily fix the bugs in VHDL as compared to Verilog. So these are the advantages. But yes, VHDL is strongly typed, mean to say whenever we are writing the code in VHDL, so code will be a little bit long as compared to Verilog. So now we are going to see some differences between the Verilog and VHDL. So Verilog used to model electronic system, however VHDL used in electronic design automation to describe digital and mixed signal system. Verilog is weakly typed, however VHDL is strongly typed, mean to say VHDL is more strict about the syntax. Verilog is based on C language, syntax is very much similar, however VHDL is based on Pascal and ADA language. Verilog is case sensitive, VHDL is not case sensitive. In Verilog we have simple data types. In VHDL data types are more complex. Verilog is a new language. Standard is 2001, IEEE 2001. However, VHDL is an old language and it has developed in 1980s. Verilog is less complex in nature. VHDL is more complex in nature. So if you are a beginner, then I'll recommend you to start with Verilog. Then it will be more easier for you to build the concept. And after some time, you should start VHDL. So Verilog supports 4 levels of abstraction: switch level, gate level, data flow level and behavioral level. So in switch level, the implementation is done in terms of switches. In gate level, we basically talk about logic gates interconnection. In data flow level, the designing has done in terms of equation. Mean to say, it is based on the data flow, how the data is flowing in the circuit. Based on that, the equation has written. And the last one is behavioral level, which is completely based on the behavior of the circuit. So one by one, we'll understand each and every level. So starting with switch level. So at switch level, a module can be implemented in terms of switches. So we can represent the entire circuit by using CMOS transistor. And here in switch level, NMOS and PMOS are used as switches for the design purpose. So we can understand with the help of a small example. So here you can see this figure is nothing but a CMOS inverter circuit. So here this is PMOS, this is NMOS, the input is A and the output is Q. 2 voltage supplies are there, VDD and VSS. So we'll first focus on syntax. So whenever we are writing a code in switch level, then the syntax will be MOS name, which can be PMOS or NMOS, then instance name. This instance name is completely optional, then the output and then data and control. Now this is the Verilog code for this circuit. So don't bother about the complete code because in upcoming lectures, I'll explain each and every point of Verilog code, what is the basic framework and how we can write the Verilog code. I'll explain each and every point. So for now, just focus on the switch level modeling, that how can we write a code in switch level. So our point of interest is this line, like how we are writing the switches. So first the MOS name, which is PMOS, then the instance name, which is P, and then the output data and control, which are Q, VDD and A. So this line is basically for this PMOS circuit. Here for PMOS, input is A, then Q, and then the data is VDD. Now for this NMOS, you can see here the MOS name is NMOS. The instance name is N. You can write any name here, and then output data and control, which are Q, VSS and A. So this is all about switch level modeling, and I hope now you got just a basic idea how you can write a code in switch level. So now we are moving towards the next level, which is gate level. So at gate level, module is implemented in terms of logic gates. Gate level is basically represents the lowest level of abstraction. The basic logic gates are available as predefined primitives. Actually, in the digital library of Verilog, these logic gates has already saved, and we can directly use those primitives like AND, OR, NAND, NOR, any gate we can use. So we'll understand that with the help of example. So here you can see the syntax. First of all, we have to write the primitive name. This primitive name is nothing but the logic gate which we are considering. Then the instance name, again it is completely optional. You can write any instance name, even you can skip this part. Then the output of the gate, and then all the inputs. So now consider this example, AND gate. Here the inputs are A and B, and the output is out. So we can write AND. One more thing guys, since Verilog is case sensitive, so whenever you are writing the primitive name, so it should always be in lowercase characters. As you can see here, I have written this AND gate name in lowercase. So always focus on this point, otherwise it will throw an error. So here the primitive name, which is AND, then instance name, I have taken G1, and then outputs and inputs. Output is out and the inputs are A and B. So in this manner you can represent a gate. You can consider another example here like NAND gate and OR gate. In this NAND gate, inputs are AB and the output is Y. So here simply I have written NAND, then instance name G2, and then input output ports, which are Y, A and B. Similarly here it is for OR gate. So this is all about gate level modeling, and really it's very simple to represent a circuit in terms of gate level, but sometimes the code will be very long because of the interconnection of the circuit. So now we are moving towards the data flow level. So whenever we are talking about register transfer level, then this data flow level comes into the picture. So at this level, module is designed by specifying the data flow, like how the data is flowing in the circuit. Based on that, we just need to write the equations. So in data flow level, signals are assigned by data manipulating equation, and design is implemented by using continuous assignment. Actually, we have to use assign statement in data flow level, and whatever assignments are there, all those assignments are concurrent in nature. So we can understand the data flow level by using this simple example. So as I told, assign keyword is used in data flow level, and here you can see in this example I have written this assign, then z equals to x and y. So this x and y is assigned to z by using this statement. Another example you can see here, assign p equals to q or r. So this q or r is assigned to p variable. So like this you can write a code in data flow level by using assign statement, which is a continuous assignment. Now we are moving towards the behavioral level. So the behavioral level is the highest level of abstraction which is provided by HDL. Behavioral level basically describes the system by its behavior. In behavioral level, different elements like functions, tasks and blocks can be used, and two important constructs are initial and always. So we'll understand the behavioral level with the help of example. So here I have taken a 2x1 multiplexer. So as we all know, in 2x1 multiplexer, the simple behavior is when the select line is high, then input I1 is assigned to output, and when the select line is low, then input I0 is assigned to out. So similarly here I have written this always at I0 I1 select. So this is nothing but a sensitivity list. So for now don't bother about this code. Actually this is not a complete code, this is just a snippet which I have taken from 2x1 multiplexer code. So I'll tell you each and everything in upcoming lectures. So for now just focus on the behavior of 2x1 multiplexer. So here I have written if select, mean to say when select line is high, then input I1 is assigned to out, and when it is low, then input I0 is assigned to out, which is the simple behavior of 2x1 mux. So in behavioral level modeling, we can define a circuit on the basis of the behavior. So this is all about behavioral level modeling. I hope you got all the concept. So a module is the basic building block in Verilog. So what is the meaning of basic building block? You can understand that with the help of an example. So consider a building, a simple building or your home. So the basic block is brick. With the help of bricks, the entire building has made. So similarly in Verilog, the module serves the same purpose. This module is the basic building block, and it can be an element or a collection of lower level design blocks. So these modules provide the required functionality to the higher level blocks through its port interface, but it hides the internal implementation. So in other words, we can say that it provides the flexibility to the designers to modify the module internals without affecting the rest of the design. So maybe few lines are just not clear to you, but don't bother about that because I am going to explain each and every term. So just consider the basic framework of Verilog code. So whenever you are writing a Verilog code for any digital circuit, then what should be the basic format? So here we are going to know about that. So as you can see here, the code is starting from module and ends with end module. So here module signifies the declaration of the module and end module signifies the termination of the module. So this is about the beginning and end of the module. Now after module, we need to write the module name. Now this module name can be anything. We can write any name, we can give any name based on the circuit. And after writing the name, in parenthesis we just need to write all the inputs and outputs, means the list of ports we just need to write here. Then we have to declare the ports, whether that port is input or output, so we have to write that. So this is about port declaration. After that we just need to write the statements, and these statements are nothing but the functionality of the circuit. It can be written in terms of behavioral modeling or in data flow level or in gate level or switch level. And last but not the least, this semicolon represents the termination of the statement. So it is very important to terminate a line. So this is all about the basic framework of Verilog code. I hope you guys are getting that. After seeing some example, it will be more clear to you. Okay, so we are now moving towards instantiation. What is the meaning of instantiation in Verilog? So instantiation allows the creation of hierarchy in the Verilog description. Here the hierarchy means with the help of some sub-modules, we are just trying to make the main module, the top block, with the help of some sub-modules. And this is nothing but the hierarchy, and it can be done by using instantiation. So it is a process of creating object from a module template, and the objects are called instances. So you can understand the instantiation with the help of a small example. Suppose we just want to represent, or we just want to design a full adder circuit with the help of half adder circuit. So we just need to write a module for half adder circuit, and then we instantiate that module 2 times to create 2 copies of that half adder circuit. So this instantiation is nothing but creating the copies of hardware circuit. In Verilog, nesting of module is illegal. Means we cannot define one module inside another module. So now we will consider an example. So here a 4x1 mux by using 2x1 mux. As I was talking about the hierarchy, so yes, here I am trying to represent a 4x1 multiplexer with the help of 2x1 multiplexer. So as we all know, 3 blocks of 2x1 multiplexer is required to represent a 4x1 multiplexer. As we can see here in this figure, 3 2x1 multiplexer block is there, this and this. 4 inputs I0, I1, I2 and I3. 4 inputs are there, 2 select lines S1 and S0, and 1 output out is there. Now how can we represent a 4x1 mux by using 2x1 mux? We can see here. So first of all, we need to write a Verilog code for 2x1 multiplexer. So now you are familiar with basic framework of Verilog code. So I hope you guys are now just capable to understand this code. So I am starting with module, then module name, which is mux221, then listing of all the ports. So here I0, I1 are nothing but inputs, then select line, which is also an input, and then out. Then port declaration, I0, I1 select is our input and out is output. Then here I am using behavioral level modeling to write the code. So always at I0, I1 select. So this is the sensitivity list, and I am using always block here. And then if select, whenever this select line is high, then I1 is assigned to out, otherwise this I0 is assigned to out. So this is representing a 2x1 multiplexer. Now our target is to describe a 4x1 multiplexer by using 2x1 multiplexer. So we just need to create 3 copies of 2x1 multiplexer, as you can see here in this figure. So now we are moving towards the main module, which is 4x1 multiplexer. So here you can see module, then mux 4 to 1, then port listing, here 4 inputs, 2 select lines and 1 output. Then port declaration, I0, I1, I2, I3 and S1, S0. Then output is out. Here one new term is there, which is wire. So for now just consider this wire X1 and X2, as X1 is output of this multiplexer and X2 is output of this multiplexer. So for this last 2x1 multiplexer, X1 and X2 are 2 inputs, S0 is select line and output is out. This is the meaning. So here I have instantiated 3 times because I just want to create 3 copies of multiplexer, 3 copies of 2x1 multiplexer. So M1, M2, M3 are the instance name, and then I have written the ports. Now to be very careful about this ports, because whatever order we have given here in the sub module, the same order we need to follow while instantiating that. So here you can see First of all, 2 inputs, then select line, then output. So same order we are following here. 2 inputs, select line, and then output. So similarly, I have instantiated 3 times to create 3 copies for last multiplexer. X1, X2 are inputs, S0 is select line, and out is out. So this is all about representing 4x1 multiplexer by using 2x1 multiplexer. So I hope that instantiation is clear to you. Now we are going to talk about Verilog keywords. So Verilog is case sensitive in nature. Although we can use underscore, dollar and alphanumeric characters to represent the keywords, but there is a proper format, and here you can see the correct format is this one. The keyword should always be in lowercase and it should not start with underscore or a number like here. This format will throw an error in your code, so avoid using this style and always prefer this style. It is recommended. So this is about the Verilog keywords. Now we'll talk about comments. So comments are basically used for the documentation purpose. Actually, it improves the readability of the code. So whenever you are writing a code, so you should always use writing comments. It is always recommended because it's very important to write why you are using that particular line. When you will open that code after 10 days or after a week or after 1 month, then maybe you will forget how that line works or why you have written that particular line in your code. So for that purpose, comments will be added to your code. So there are 2 types of comments, single line comment and multi-line comment. Whenever you just need to write single line of comment, then you should use this double slash. And in case of multi-line comment, you can start that with this slash and asterisk sign, and you can close with asterisk and slash. So this is all about comments. We can understand it with the help of example. So here in first line I have given single line comment. So here I am using double slash and write the comment. One more thing guys, this comment will not be considered for the simulation. Your statement will be terminated here. So whatever comment you want to write, you can write by using this double slash. And in case of multi-line comment, you can start with slash and asterisk sign, and you can terminate that by using asterisk and slash. So this is multi-line comment. So starting from simulation is used to verify the functionality of the digital design that is modeled using HDLs like Verilog. So simulation is basically to verify whether your code is working correctly or not. Suppose you have written an RTL and you just want to check whether your code is working properly or not. So for that purpose, you can perform simulation. And for that simulation, you just need to write the test benches. Now, what is test bench? In test bench, we give a set of inputs called stimulus. And whatever outputs are generated with the given input, we just evaluate whether the circuit is working correctly or not with the help of those generated output waveforms. And this complete process is called the simulation. So for simulation purpose, we apply different input stimulus to the design at different time to check whether the RTL code behaves in intended way or not. So we just need Verilog module, which is RTL, and then test bench. With the help of these 2 things, we can perform the simulation, and whatever output has created after simulation, we can evaluate the result, whether the RTL is giving correct result or not. So this is all about the simulation. Now we'll talk about the synthesis. So synthesis is a process in which digital design that is modeled using HDL is translated into an implementation consisting logic gates. So in simple words, we can say that synthesis is used to convert the RTL into netlist. It will just make an optimal design based on the working strategy which we are using, and also give the consumption of resources as available. So yes, in case of synthesis, we just require Verilog module. There is not any kind of test bench. So for synthesis operation, we use RTL, and we can use either ASIC or FPGA to perform the synthesis operation. So most of the people have seen the FPGA board in your college lab. It is a green color board, and we just need to dump the program into that board, and we can check the functionality. We can check whether the RTL is working correctly or not. So this is all about the synthesis process. One more thing, in synthesis, since we are not giving any test bench here, so there is not the concept of time delay in case of synthesis, because already we are verifying the functionality on hardware. So time delay is only considered in case of simulation and not in synthesis process. So now we'll talk about the design methodologies. So in Verilog, there are two types of design methods, top down and bottom up. So in top down, the flow of design is from top to bottom. We are starting from top level block, and then we are dividing each and every block into sub blocks until we reaches to the leaf shell, which is the smallest possible block. And in bottom up design, we just start from the bottom level, that is from the lowest possible block, and then we combine those blocks to make the macros, and these macros will again combine to make the top level block. So here the flow is from bottom to top. So one by one we'll talk about in more detail. So starting from top down design method. So here we first define the top level block and then identify the sub blocks necessary to build the top level block. These sub blocks are further subdivided until we come to the leaf cell, which cannot be further divided. So here you can see in this figure, we have the top level block, this one. So we have divided this top level block into sub blocks, and again these sub blocks will be divided into leaf shell, and leaf shell is nothing but the smallest possible block which cannot be further divided. So here the flow is from top to bottom, and that's why this methodology is called top down design methodology. The design is flowing from top to down. Now we'll talk about bottom up design methodology. So here we first identify the building blocks that are available to us, and then we just combine these building blocks to build a bigger block. So these cells are then used for higher level blocks until we build the top level block in the design. So here you can see in this figure, we just check what are the blocks which are available to us. So here these leaf shells are available to us. So we just combine these smaller blocks and make the macros. Now these macros will again combine to form the top level block. So here you can see the flow is from bottom to top, and that's why it is called bottom up design methodology. We are starting from bottom level, from smallest possible block, and then we are moving towards the top level block. So I hope it is clear to you. So guys, talking about the data types. So a data type in programming is a classification that specifies which type of value a variable has and what type of mathematical relation, like logical operation or arithmetic operation, we can apply to it so that it will not cause any error in the system. So this is about the data type. Now talking about the data types supported by the Verilog, then there are mainly two data types, register and net. So one by one we'll cover. So starting from register data type. So register data types are mainly used to store the values. It holds the value, but it doesn't mean that it's going to produce hardware register. This data type is totally different from hardware register. It is simply a data type which can hold a value until we assign a new value to it. It is commonly declared by the keyword reg, and the default value of reg data type is unknown, which is X. In register data type, there are different classes like reg, integer, real, time. So we'll cover in upcoming lectures. So now we are moving towards net data type. So nets represent the connection between the hardware elements, and it must be continuously driven. Mean to say, it cannot be used to store the values. Nets are declared primarily with the keyword wire, and the default value is Z. Again, the net data type has different classes like wire, then wired and, wired or, try, and, try or, try reg. So we'll cover all these classes in upcoming lectures. So now we are moving towards values and signal strength. So Verilog supports 4 different value levels, and these are 0, 1, X and Z. So 0 represents logic 0, means false condition. 1 represents logic 1, which is true condition. X represents unknown logic, and Z represents high impedance. So this is about the value levels. Now talking about the strength levels, so Verilog support 8 different strength levels, and these are supply, strong, pull, large, weak, medium, small and high Z. And here in this table you can see the strength level is increasing from bottom level to top level. Means as we are moving from bottom to up, the strength level is increasing. Now the twist is that when we apply 2 different strength level signals as an input to the wire, then this higher strength level signal will be reflected at the output. And when we apply the same strength level signals as an input to the wire, in that condition the output will be unknown. So you can understand from this figure. In first example, I have given 2 inputs, supply 1 and pull 1, and you can see at output the supply 1 has reflected, and the reason is supply 1 has a higher strength level as compared to the pull 1. In second example, I have given 2 inputs, strong 1 and strong 0. Since both the signals are in same strength level, so in output there is unknown value. So yes, I was talking about these 2 conditions. Now we are moving towards the last topic of today's lecture, which is port assignments. So we have 3 different types of ports: input, output and in-out. Inputs and outputs are unidirectional, however in-out ports are bidirectional in nature. Talking about the input port, so within the module it is of wire data type, but externally when we assign any variable to this port, then it can be of reg or net data type. Now talking about the output port, so yes, internally it can be of reg or net data type, but externally it is always be of net data type, that is wire data type. Now in in-out ports, it is always be of wire data type. We can never assign reg data type to the in-out port. So this is all about the port assignment. So nets basically represent the connection between the hardware element. It must be continuously driven, mean to say we cannot use a net data type just to store the value. the keyword which is used for net data type is wire and the default value is Z. There are different classes in net data type and these are wire, wired and, wired or, try, try and, try or, try reg. So one by one we'll cover these classes in detail. So starting from wire. So here you can see in this AND gate the inputs are A and B and the output is C. So here the output C is net data type, mean to say it is continuously driven. As we'll give the different values at the input side, according to that the output value will change. It will not store the value because it is continuously driven. So here I have taken a half adder circuit. The inputs are A and B and the outputs are sum and carry. So here in Verilog code, you can see module name is half add, then the different ports are A, B, sum and carry. Then I have just written the port declaration, input A comma B, output sum comma carry. Now I have taken this sum and the carry as a wire data type and then I am using assign statement. As we have seen in a previous chapter that with assign keyword the left hand side variable should be of wire data type. We cannot use a reg data type here. That's why we have taken sum and carry as a wire data type. Now A XOR B value is assigned to sum and A and B value is assigned to carry. So this is about the Verilog code of half adder circuit using wire data type. Now we can see there are different classes like wired or, wired and, supply 0, supply 1. So what are the advantages of wired or and wired and? So we'll cover that. So here in this diagram you can see two gates are there, and or. In AND gate, two inputs A and B, and in OR gate, two inputs C and D. And the output of both the gates are just connected and the final output is Y. Now the problem in this circuit is that if we use simple wire data type for output Y, then it will give an indeterministic value because we are assigning two different values to the output Y, A and B and then C or D. So simulator will get confused that which value it has to just assign to the output Y. But if we use wired and or wired or for output Y, then this problem will not be there. Because in case of wired and, as you can see in the second example, I have taken wired and logic here. So the final value which is assigned to output Y is the AND of A and B and C or D. As you can see here in this block, Y is nothing but the AND of A and B, C or D. So here the output will be more accurate, not an indeterministic value. Similarly, you can use wired or also here. So this is about wired or and wired and. Now in this example, we'll get an idea about supply 1 and supply 0. So here in this Verilog code, I have taken 4 inputs A, B, C, D and 1 output Y. Then supply 1 VDD and supply 0 ground. Then different logic gates are there, OR and XOR, and accordingly I have given input and outputs to these gates. So this is about the supply 0 and supply 1. I hope you got the idea that how you can use supply 0 and supply 1 while writing the Verilog code. Now we'll talk about the numbers, that how you can represent a number while writing a Verilog code. What is the correct format? So the syntax is size, single quote, then base and then number. So here size is nothing but total number of bits. and base represent the base which you are using for that number, and then the actual number. So here in first example you can see I have written 1 tick B1. So here 1 is representing the total number of bits, which is 1, and B is representing the base, which is binary. So this is nothing but a logic 1. As you can see here, it is a 1-bit number. Similarly, in second example, I have written 8 tick H21. Now here this 8 is representing total number of bits, that is 8, and H is nothing but the base value. So here the base is hexadecimal, and as we all know, in hexadecimal we represent a number by using 4-bit binary. So here for 2 will represent that by using 4 binary bits, and 1 is also represented by using 4 binary bits, as you can see here. So this is nothing but an 8-bit number. Similarly, in third example also I have given 12 tick H A35. So 12 is nothing but 12 bits, then H is the base, which is hexadecimal. So here we have to represent each number by 4-bit binary, as you can see here. So this is about the basic syntax of the numbers and the understanding that what it is representing. Now we'll talk about some more points. So here you can see for binary we have to use B, then for octal it is O, for decimal it is D, and for hexadecimal it is H. These we have to use while giving the base value. Now we'll talk about the use of underscore while writing a number. Actually, underscores are used to improve the readability of the code. Whenever we are talking about a 64-bit number or a 32-bit number, then total number of bits are really large and it will not be that readable. So just to improve the readability, you can use the underscore to represent the number. As here you can see, it is more readable. Okay. And now we will talk about the extension, which is 0, X and Z extension. So in first example, I have written 4 tick B X0. Actually, the basic concept behind the extension is that whatever the total number of bits here, we have to complete that. And when the number here is not completing the total number of bits, then we use the extension concept just to complete the total number of bits. So here I have written 4 tick B X0, so it is representing a 4-bit number and the base is binary. So total 4 bits should be there, but here we can see base is binary and the number is X0. So this is 0, this is X, but still only 2 bits are there. 2 more bits should be required to represent the number in 4 bits. So here we simply extend the left hand side number to complete the 4 bits. So this is nothing but the X extension. Similarly, in second example, I have written 5 tick D1. Now the 5 is nothing but total number of bits. So here in this number, the total bit should be 5 and the base is decimal. So in decimal, the number 1 can be represented as 1. But still the total number of bits should be 5. So just to fulfill that, we have to extend by using 0. So here we are using 0 extension to complete the total number of bits. Now in third example, I have written 16 tick H Z6. So here total 16 bits should be there, base is hexadecimal, so again we have to represent each number by using 4 binary bits. So for 6 I have written 0110 and for Z 4-bit Z. But still there is only 8 bits and we require 16 bits. So just to fulfill the 16 bits, we are using Z extension here. So now you can see the total number of bits are 16 here. So this is about the 0, X and Z extension. I hope you got the idea. So Verilog supports different register data types and these are reg, integer, real and time. So reg data type is the most widely used data type. Talking about the integer, so it is basically used for the loop counting purpose. Real data type is used to store the floating point numbers, and the time is used to keep track of the simulation time. So one by one we'll understand. So starting from basic introduction of register data type. So it is used for the data storage purpose. It can hold the value and it is declared by the keyword reg. The default value is unknown, and the different classes of register data types are reg, integer, real and time. So here we'll see an example of reg data type. So here you can see you can declare a reg data type in single bits or in multiple bits. So in single bit, simply you have to write reg and then the name of the variable. So it will represent a single bit register variable. Now in case if you want to declare a register data type as a multiple bit, then you have to write reg, then the size and then the name of the variable. So here it is representing an 8-bit buses because of this size. So now see this example. Here I have taken reset as a register data type. Then in initial block I have assigned different values to the reset variable. So initially the value is 0, then after 10 time units delay I have assigned the value 1, and then again after the 10 time units delay the value is 0. So here the meaning is, since reg data type stores the value, so initially this reset will have the value 0, and at 10 time units the value is changes to 1, and then this variable holds the value 1 until it will get the another value 0 at additional 10 time units. So this is the meaning of the register data type. Now we'll talk about the integer data type. So it is a general purpose register data type, and it is declared by the keyword integer. It stores the values as assigned quantities. Mean to say you can assign negative and positive both the numbers to the integer data type. It is generally used for the counting purpose, and it is synthesizable in nature. The default value is unknown and the default width is 32 bits. Mean to say, if you are not giving any width while declaring the integer data type, then by default it will be 32 bits. Now consider this example. Here I have taken count and new num as an integer variable, and then I have assigned the values. For count it is 4 and for new num it is -17. So here you can see how you have to declare integer variable and how you can assign the values to the integer variables. Now we'll talk about the real data type. So the keyword real is used to declare the real data type. It allows decimal and scientific notation, and it is mainly used to store the floating point numbers. It is non-synthesizable in nature, mean to say it cannot be used for synthesis purpose, and the default value is 0.0. Whenever we assign a real number to the integer variable, in that condition the value will be rounded off to the nearest integer. Consider this example. Here I have taken two real variables, count and new num. This is the declaration, and here I have assigned the value. For count it is 4.76 and for new num it is -1.3. Now here you can see A and B are two different variables. A is of integer data type and B is of real data type. Now for B the value is -6.5. I am assigning this real number to the integer variable. So the real number will be rounded off to the nearest integer. So the value of integer A will be -7 here. So I hope you got the point how we can round off the value to the nearest integer. So this is all about the real data type. Now we'll talk about the time data type. So it's a special time register data type which is used to store the simulation time. It is declared by the keyword time. Time variables are unsigned in nature and width is generally 64 bits. It is non-synthesizable in nature and the default value is unknown. So whenever I am telling that this particular data type is non-synthesizable in nature, so the meaning is that whenever you are performing the synthesis operation, then that variable will be just ignored by the system. Now consider the example of time data type. So whenever we are talking about the synthesis, so in that condition we are just implementing the real gates. We are using the real gates. So at that time there will not be any use of time delays or this time data type. The actual delay of the gate will be considered in that condition, and that's why we are telling that the time data type is not synthesizable in nature. Now consider this example. Here I have taken this new sim time variable and this is a time data type, and here I have assigned $time to this variable. Now this $time is nothing but the system function which gives the current simulation time. So here simply the current simulation time will be stored to this variable. So starting from vectors, so nets or reg data type can be declared as a vectors. Mean to say, you can declare reg or net data type. It can be of 1 bit or it can be of multiple bits. So if bit width is not specified, then the default size is scalar, mean to say 1 bit. These vectors represent the buses, and vectors are declared and it is specified by the range R1 and R2. So here you can see this R1 is nothing but the MSB and the R2 is nothing but the LSB. So in this example you can see the first one is wire XYZ. So it is nothing but the single bit variable because I have not given any vector here. So by default it will be scalar, that is 1 bit. In second example I have written wire 15 down to 0 data. So here data is a 16 bit data. In third example I have written wire then 0 to 31 sum. So here sum is a 32 bit data. As I have told, this 0 is representing the MSB and this 31 is representing the LSB. Similarly here also this 15 is nothing but the MSB and 0 is nothing but the LSB. So remember just one point, whatever is there at the left hand side, that is representing the MSB, and whatever is there at the right hand side, that is representing the LSB. This is the simple idea. Now we'll talk about the arrays. So in Verilog, arrays are allowed for reg, integer, time and real data types. Whenever we are declaring the multi-dimensional array, we can declare it with any number of dimensions. Here you can see a very important difference, and it can be asked in your exam or in your viva that what is the difference between these two representation. So just understand it carefully. So the first representation is nothing but a register bank. Here I have written reg 7 down to 0, register bank 15 down to 0. So this is representing 16 8-bit registers. However, in second example, I have written reg num 31 down to 0, and this is representing an array of 32 1-bit numbers. So you can see the difference. First one is 16 8-bit registers and the second one is an array of 32 1-bit numbers. So I hope you got the idea. Now here I have considered the different array examples. First one is representing the one-dimensional array. Here I have taken reg, then the array name which is reg A, and then the vector which is 0 to 7. So here it is representing an array of 8 1-bit registers, as you can see here. This is a one-dimensional array. Similarly, here I have taken, but this is a 2-bit array. Similarly, here I have taken another example. This is representing a 2-dimensional array. So reg, then array A, which is the array name, and then the dimension. So you can correlate this with a matrix. In matrix we have rows and columns, so here also you can consider this vector for rows and this vector for columns. So in this figure you can see the 2 rows, this, and 4 columns, 0, 1, 2, 3. Similarly, here I have taken another 2-dimensional array which is wire, array W, 0 to 7 and 0 to 3. So here total 8 rows are there and 4 columns are there. Now we'll talk about the memories. So memories are modeled as a one-dimensional array of registers. So it is basically used to model register files, ROMs and RAMs. Each element of the array is known as the element or a word, and you can address these elements by using the index number. These elements can be of 1 bit or it can be of multiple bit, as I have just explained in the vectors part. Now you can see here we generally use one-dimensional array for the memory purpose. So here you can see this is reg, then mem 1 bit, 0 to 1023. So this is representing a memory mem 1 bit with 1k 1 bit words. So here this 1k is nothing but the depth, and each element is of 1 bit. Similarly, in second example I have taken reg 7 down to 0, mem byte 0 to 1023. So this is representing the 1k memory, mean to say width is 1k and each element is of 8 bits. This is the meaning. So simply just the idea is the first vector is representing the width, like this thing, and the second vector, which is the last one, is representing the depth of the memory, which is this one. So hope you got the point. Now we'll talk about the parameters. So parameters cannot be used as a variables. It is a constant value. So now the question arises, if we can simply declare a constant, then why we should use parameters and what are the advantages? So the thing is that if you are using parameters and if you are declaring some variables as a parameter, then it will help to customize your code. Consider an example of memory designing. If you are designing an 8x16 memory, here the width is 8 and the depth is 16. So you will write the code according to that. After some time, if you want to write the code for 16x256 memory where the width is 16 and the depth is 256, so simply by changing the parameter values, you can change the entire code for the next block. Mean to say, you will not need to make the changes in that code, just you have to make changes in the parameter value, and here you have done. So this is the advantage of parameters. Now the last topic of today's lecture is the string. So strings can be stored in reg. Strings are nothing but the all about the characters. Basically we'll talk about the sequence of characters in strings. So each character is represented by 8 bits and these sequence will be enclosed by the double quotes. So here you can see I have declared a string which is string value, and this is a register type string, and the vector I have taken is 8 into 10 down to 1. Now the reason of taking this vector is this one. Now the reason of taking this vector is because Each character is of 8 bits, and here I am assigning 10 different characters, so that's why here I have taken 8 into 10. So this is about the declaration of string. Now we have to assign a value to this string variable. So here I am assigning this VLSI point to the string variable. So like this you can declare a string and you can assign the sequence of characters. There are some special characters of string like \n, which is used for the new line, \t for the tab, \%, which represents the percent, then double backslash is used for the single backslash, and double quote is used for the double quotes.
In any programming language like C, C++, Java, there are some operators which are built in that language. It can operate on some data items like numbers, characters, and some values. In Verilog, there are set of operators, and some of them are very similar to high-level languages like C and C++. But some of the operators are more specific in case of Verilog, which have direct connection with hardware that Verilog is supposed to model. So operators act on operands to produce desired result. Now different types of operators are there in Verilog, and these are arithmetic operators, logical operators, bitwise operators, then equality, relational, reduction, shift operators, and then concatenation and conditional operator. So one by one we will cover each and every topic. So starting from arithmetic operators. So there are two types of arithmetic operators, unary and binary. So unary operators, here the operators plus and minus can work as unary operators. So basically it is used to determine whether the operand is positive or negative. So here in this example I have shown -4 and +5. So in this manner you can represent a number whether it is a positive number or negative number. So this is the use of unary operators. Now we will talk about the binary operators. So binary means 2. So in binary operators we consider 2 operands and then perform different binary operators. And these are add, subtract, multiply, divide, modulus and exponential. So we will understand these things with the help of some examples. So here I have taken A and B as a register vectors and then few integers D, E and F. Now in first example it is A multiplied with B. So A is a 4-bit value, 4 tick B 0010, and B is also a 4-bit value, 4 tick B 0011. Now when you perform the multiplication operation between A and B, then you will get the answer 4 tick B 0110. Guys, I am requesting you to solve each and every example on your copy and then match the answer with my answer. So in this manner you will get how you can perform these operations. Okay, so in second example, here I am taking this D divided by E. So here the D value is 7 and the E value is 4. So when you will divide this D by E, then the result will be 1. Now the value will be truncated. Also you can perform A plus B, B minus A and then E exponential F. So in this manner you can perform different arithmetic operations. Now here I have considered some examples with unknown values. So remember one thing, if you are using arithmetic operators and if one of your operand or both of the operand is having unknown value, then your final result will be unknown only. Even if the single bit is unknown, then also the overall result will be unknown in case of arithmetic operators. Here you can see value of A is 4 tick B 001x and B value is 4 tick B 1011. Now the sum equals to A plus B. So when you will perform the addition operation, then the final result will be unknown because one of the operand is consisting unknown value. So the overall result will be unknown only. Also, here I have considered some modulus operators also. So 17 modulo 4 and the result will be 1. So whenever you will divide 17 by 4, then the remainder will be 1. So here the answer is 1. Similarly, 16 modulo 4, here the answer will be 0. Then minus 7 modulo 2 and 7 modulo minus 2. Now the last two examples are really very important. So focus on these examples. Whenever your any one operand is negative, either first or second, then the answer will be according to your first operand. Basically the sign of the result. Whenever the sign of first operand is negative, then the overall result will be negative only. And when the first operand is positive, then the overall result will be positive only. So here you can see this is minus 7 modulo 2. So the result will be minus 1. Why minus sign? Because of this first operand. Similarly here 7 modulo minus 2. So here the result is plus 1. So why this plus? Because of this first operand. So in this manner you can perform the arithmetic operations. Now we are moving towards logical operators. So we use logical operators to define the conditional statement. The result of logical operators is always true or false. So when it comes to define the conditional statement, like if then given condition. So when the condition is true, then do this, else do that. So in that kind of situation, we use logical operators. Now different types of logical operators are there, and these are logical negation, logical and logical or. Consider the example here. So A value is 5 and B value is 0. So here in first example, I have taken A, logical and B. Now here I can see the A value is true but the B value is false. So the overall result will be false only. Similarly, A, logical or B. So in case of logical or, if either of the operand is high, then the overall result will be high only. Then negation A and negation B. Since A is high, then its negation will be logic 0. And B is a false value. So its negation will be logic 1 only. Similarly, some unknown values like here A is 2 tick B 0x and B is 2 tick B 10. So whenever you perform A, logical and B, so the result will be unknown only because one of the operand consists this unknown, and because of this the overall result will be unknown only. So this is all about logical operators. Now we will talk about the bitwise operators. So bitwise operators performs the operation between the bits. It performs bit by bit operation on two operands. It takes each bit in one operand and then perform the operation. So different types of bitwise operators are bitwise AND, bitwise OR, bitwise negation, then bitwise XOR and XNOR. Here you can see the table for bitwise AND, OR, XOR, XNOR and negation. I have considered three values 0, 1 and unknown, and according to the table you can see whenever you are performing this bitwise AND, then what result you will get in case of bitwise OR and other bitwise operators. So here in these examples you can see X, Y and Z values. Whenever you perform this negation of X, so X is nothing but a 4-bit value, 4 tick B 1010. And whenever you want to perform the negation operation, so we need to perform the negation of each bit of X value. So the result will be 4 tick B 0101, and this is nothing but the negation of these bits respectively. Similarly here X and Y. So here we have to perform the AND operation between X and Y, and this is nothing but the bitwise AND operation. So the result will be 4 tick B 1000. Similarly here x or y, so we need to perform the OR operation between x and y. Similarly, you can perform the other operations like x XOR y, x XNOR y, x and z. Now here, since this z variable consists this unknown value, so here when you perform the AND operation between x and z, so the second bit, this one, the result will be unknown only, because when you perform the AND operation between unknown and 1, so the result will be unknown only. So here the final result is 4 tick B 10x0. So this is about the bitwise operators. Now we will talk about equality operators. So basically we have two types of equality operators, logical and case. Logical equality, logical inequality. Then case equality and case inequality. So logical equality is synthesizable in nature. However, case equality and inequality is non-synthesizable in nature. The result of equality operator is logic 1 or logic 0. Mean to say it will be of single bit only, either true or false. The important difference between the logical equality inequality and the case equality and inequality is that in case of logical equality, we will not consider x and z values. However, in case of case equality, we consider the x and z values. Here you can see the symbol for equality and inequality. Now in most of the interviews, the interviewers may ask this question that what is the difference between this double equals and triple equals sign. So here you need to say that double equal is indicating the logical equality and the triple equal sign is indicating the case equality. Okay, so here you can see the examples. A value is 4, B value is 3, and whenever you will check whether A equals to B. So if this expression is true, then the result will be true. That is logic 1. And if the result is false, mean to say if the expression is false, then the result will be logic 0 only. So here you can see A is 4 and B is 3. So these two values are not same. So this expression is false. So the result will be logic 0 only. Similarly here x not equals to y. So we need to check whether this expression is true or false. So x value is 4 tick B 1010 and y value is 4 tick B 1101. So these two values are not same, and according to this expression x is not equal to y. So this expression is true. So the result will be logical 1 only. Similarly, x equals to z. We have to check whether the x is equal to z or not. So here the z is 4 tick B 1 xxz. Now we are using the logical equality, and this logical equality can't consider the x and z values. So here the result will be unknown only. Whenever you are applying the logical equality or inequality and your operands consist the unknown or high impedance value, in that condition the result will be unknown only. Similarly here I have taken the case equality. So whether this z is equal to m or not, including x and z. So you can see this z is 4 tick B 1 xxz and m value is 4 tick B 1 xxz. So both the values are same. So here this expression is true. So the result will be logical 1 only. Similarly here z equals to n. Whether this expression is true or false. So this is false. You can check here the z and n values. These two values are not same. So the result will be logic 0. So in this manner you can perform the equality operations. Now we will move towards the relational operators. So 4 types of relational operators are there: greater than, less than, greater than or equal, less than or equal. Also, it returns a logical value, either true or false, mean to say a single bit output value. Here you can see the symbol for relational operators, and then we will consider some examples. So here A is 4, B is 3. Now we have to check whether this A is less than or equal to B or not. So you can see this expression is false because A is greater than B. So here the result will be logical 0 only. Similarly here A greater than B. So we can see A is 4, B is 3. So this expression is true. So the result will be logical 1. Then Y greater than equal to X. So we can see Y is 4 tick B 1101 and X is 4 tick B 1 triple X. So we have to check whether the result will be logic 1 or logic 0. So here in this third example, you can see the expression is Y greater than equal to X. Now the Y value is 4 tick B 1101 and the X value is 4 tick B 1010. So yes, Y is greater than X. So the result will be logical 1. Now, in the last example, the expression is Y less than Z. Since the Z value consists the unknown, 4 tick B, 1 triple X. So, we cannot determine whether the Z is less than Y or greater than Y because of this unknown, and the final result will be unknown. So, I hope you got this point. Now, we will talk about the reduction operators. So we have different types of reduction operators like AND, OR, NAND, NOR, XOR and XNOR. So in case of reduction operators, we consider the single operand. It performs the bitwise operation on a single vector operand and then yield the 1-bit result, either true or false. So here you can see the symbols for reduction operators, reduction AND, NAND, then OR, NOR, XOR and XNOR. Then we will understand this operator with the help of some examples. Here I have taken X equals to 4 tick B 1010. When you will perform the AND operation of this X, then simply the AND operation between the bits of X. So 1 and 0 and 1 and 0 and the final result will be 1 tick B0. Similarly, you can perform the OR of X. So bitwise OR operation we have to perform. So 1 or 0 or 1 or 0 and the final result will be 1 tick B1. So in this manner you can perform the reduction operation. Also reduction XOR and XNOR can be used for even or odd parity generation of our vectors. So now we'll talk about these shift operators. So shift left, shift right or arithmetic shift left, arithmetic shift right. So we have 4 types of shift operators. So in case of regular shift operators, whether it is shift left or shift right, the vacant bit positions are filled with zeros. However, in case of arithmetic shift operators, it uses the context of the expression to determine the value with which we can fill the vacated bit. Mean to say, in case of arithmetic shift operation, we have to check whether the given number is signed or not. And according to that, the vacant bit has filled. So it will be more clear when you will see the example. So here the X is 4 tick B 1100. When you will perform the 1-bit shift right operation, so the result will be 4 tick B 0110. So whenever you will shift this number right side by 1 bit, so here I have filled the MSB bit. MSB means this bit, final bit. So this bit is filled with 0 because of this regular shift operation. Similarly here, when you will perform the 1-bit left shift operation, so in that condition also, the LSB position is filled with 0. But when we consider the arithmetic shift operation, so in that condition, so here, if we consider this X value as a signed number and then we want to shift this X value right side by 1 bit, then the result will be 4 tick B 1110. So here the vacant bit is filled with 1. Why? Because of this MSB bit. So I hope this example is clear to you. Also, integers A, B and C, and we are considering these as a signed data types. Now A is 0, B is minus 10 and C is nothing but A plus 3-bit arithmetic right shift of B. And then we have to perform the addition of these two. So here the result will be minus 2 of decimal. And this is because of the arithmetic shift. You can check by solving these examples and you can match your answers. Now we'll talk about the concatenation operators. So basically it provides a mechanism to append multiple operands. The operands in case of concatenation operator mean to say we cannot use unsized operands in case of concatenation operators. Also, these operands can be scalar nets or registers or vector nets or registers. So consider this example here. A, B, C and D, 4 variables. Then I have taken y equals to B comma C in concatenation operator. So here order wise we need to put the B and C values. So B is nothing but 2 tick B 0 0 and C is nothing but 2 tick B 1 0. So here the final result will be 4 tick B 0 0 1 0. Similarly, in second example, A comma B comma C comma D, then 3 tick B 0 0 1. So here we need to put the values as per this order. So first of all A value, then B, then C, then D and then this 3-bit value 001. So the final result will be 11 tick B 10010110001. So here we are nothing but appending the bits. In third example, I have written A comma B of 0 and then C of 1. So B of 0 nothing but the 0th bit of B variable which is 0 and C of 1 is nothing but the first bit of C variable which is 1. So the final result will be 3 tick B 101. And this last example here A comma, now this is the replication operator. Here the B value will be replicated 2 times. Similarly here the C value will be replicated 3 times. So the final result will be this one. So you can check by solving this expression. So this is about the concatenation operator. Now we will talk about conditional operators. So it consists 3 operands: condition expression, then true expression and false expression. So first of all we need to check this condition expression. If this expression is true, then the output will be nothing but this true expression. Otherwise the result will be false expression. This conditional operator can be of nested type, mean to say here in case of true expression and false expression, again we can use the conditional operator. So nesting is allowed here in case of conditional operator. Conditional operators is very much similar to multiplexer. You can compare this operator with multiplexer. So here I have taken 2 to 1 multiplexer. The select line is conditional expression. So when this conditional expression is true, then this true expression will be assigned to out. Otherwise, this false expression will be assigned to out when this conditional expression is false. So I hope you got the idea. Now this is the last topic of today's video, which is the operator precedence. So whenever multiple operators are there in a given expression, then you need to remember this table. What is the precedence of different operators? So here you can see the unary operators has the highest precedence. Then multiply, divide, modulus, then add, subtract, shift, relational, equality, and then reduction. In case of reduction operator, you can see here and then XOR, XNOR, and then OR and NOR. So this is the precedence from lower to higher. Then logical and conditional. So it's better to use parenthesis whenever there are multiple operators. So question 1 is, find the value of A and B from the given expression. Here A is 1 bit right shift of Y and B is 1 bit right shift of Y. But the difference is, in first case there is logical right shift operator. However, in second case, that is B value, there is arithmetic right shift operator. And the y value is 1101. So simply you have to use the logical operator first and then the arithmetic shift operator. So quickly pause the video and solve the question, and then you have to match your answers with my solution. So I hope you have solved the question. So let's come to the solution. So yes, a value is nothing but the logical right shift of y by 1 bit. So whenever you are shifting the y value by 1 bit, so you have to append 0 value in MSB position, because we have already discussed this thing in operators video. Okay, so here you will get y is 1101. When you will shift this value by 1 bit towards the right side, then the value will be 110, and in MSB position the value will be 0. So here we insert the 0 value. So the final value of A is 0110. Similarly, in second case, there is arithmetic right shift operator. So when you will shift the given number by 1 bit towards the right side, then because of the arithmetic shift operator, the MSB position will be appended with the 1. So here the y is 1101. After shifting, it will be like this, and the MSB bit will be 1 again. So this difference is because of the logical right shift operator and arithmetic right shift operator. So the question 2 is, if p is a vector of length 10 bit, then find the value of p for the given expression. So here you can see this is the concatenation operator, and I have explained very well in previous video what is concatenation operator and how we can use that operator. So here simply you have to concatenate different values, which is 2 tick b x1, then 3 tick b 101, then 2 tick b 10, and then there is a replication operator. So you have to replicate 1 tick 1 2 times. So let's see what will be the final value of p. So I hope you have solved the question, and now we can see the solution. So simply there is a concatenation operator. So the p value will be, first of all, 2 tick b x1, then 3 tick b 101, then 2 tick b 10, and then the replication operator, which is 2 times 1 tick b1. Since this p is a 10-bit number and here we are getting 9 bits only, so we need to insert the 0 in MSB position. So now this is the complete answer. The p value is 0x110111011, means 10-bit number. I hope you got the same answer. Now coming to question 3. Question 3 is, find the value of q for the given snippet. Here m is 2 tick b 10 and n is 2 tick b 1x. Now we have to assign to q variable, and there is a conditional operator, and here the expression is if m is less than n. If this expression is true, then we have to assign 2 tick b 10 to q. Otherwise, in case of false expression, the q value will be 2 tick b 11. So simply you have to check whether the m value is less than n or not, and according to that you can assign the q value. So quickly solve the question and then match your answers. So I hope you got the answer. Here, since we are using the relational operator, and in my previous video I have already explained that relational operator is not able to merge x and z values. So simply here the result will be 2 tick b xx. Why? Because this relational operator will not consider the x value, and because of that the answer will be unknown only. Now the question 4 is, evaluate the value in the given snippet. M is 5 tick b 10x1z and n is 5 tick b 10x1z. Simply you have to check whether these two numbers are equal or not. In first case there is normal equality, and in second case there is a arithmetic equality. So apply the operator and get your answers. Hope you have solved this question. Now we can see the solution. So in first case, you have to check whether the m is equal to n or not. There is normal equality. So m is 10 x1z and n is 10 x1z. Since both the value is same, but this equality operator cannot consider x and z values, and because of that the answer will be unknown only. But in second condition, where we are using the arithmetic equality operator, m and n value is exactly same. You can see here 10 x1z m value and n value is again 10 x1z. So m and n both are same including x and z values. So the answer will be 1 here. So here you can see the difference because of the normal equality and arithmetic equality. Now coming to question 5. Question 5 is find the value of Q for the following snippet, given that A is 4 tick B 0101 and Y is 4 tick B 1100. Here I have taken 4 bits variables. So there are register type variables Q, A, Y, and then we have to assign Q value A or Y. So here simply you have to perform bitwise OR operation between A and Y, and yes, you will get your answers. So quickly perform this operation. So bitwise OR operation you have to apply. A is 0101 and Y is 1100, and OR operation we have to perform. So starting from LSB side, 10 the answer will be 1, 00 the answer will be 0, 11 the answer will be 1, and 01 the answer will be 1. So the final value of Q is 4 tick B 1101. So this is all about the simple bitwise OR operation. Now talking about question 6. Question 6 is output value of C and F in the given snippet. So in this snippet, you can see I have taken 3 variables, basically register type variables, and these variables are of 4 bits. Then 3 integers D, E, F. So A value is 4 tick B 0011 and B value is 4 tick B 0001. D is 7 and E is 3. Now simply A plus B value is assigned to C and F is D divided by E. So quickly solve this question. So I hope you got your answers. Now we can see A is 0011 and B is 0001 when we perform the addition. So basically this example is the use of arithmetic operators. How you can apply the arithmetic operators on given variables, you have to check that. So we have to perform the addition. So when you will add A and B, then you will get the answer 0100 starting from LSB side. So here 1 1 the sum will be 0 and the carry will be 1. So the carry bit 1 and this one. So sum will be again 0 and the carry will be 1. So the carry 1 and 0 0. So finally the sum will be 1 only, and here this is 0. So the final value of C is 4 tick B 0100. This is the final value of C. Now F value, it will be truncated to 2. Because when you will divide 7 by 3, then you will get something 2 point something value. But F is an integer, so we have to consider the integer part only. So the final value of F is 2. So I hope you got the correct answers and you have enjoyed today's video. If you have any doubt, then you can post in the comment section and share the video as much as possible.
So talking about the gate primitives, in Verilog there are some predefined inbuilt gate primitives, and this gate level modeling is the lowest level of abstraction. All logic circuits can be designed by using logic gates. So there are two different types of gates. In basic gates, there are AND OR gates and buff NOT gates. So one by one we will discuss. Okay. So starting from basic gates. In AND OR gates, one scalar output and multiple scalar inputs are there. Output of the gate is evaluated as soon as one of the input changes. The AND OR gates available in Verilog are AND gate, OR gate, NAND gate, NOR gate, XOR and XNOR gate. So here you can see the symbols of these gates. Different gates have different symbols. And talking about the truth table, 4 different values 0, 1, X and Z. And according to the gate, you are getting the output. Since these are very basic gates and generally we are using these gates, so I hope these truth tables are clear to you. First of all, you have to write the primitive name, then instance name, and then output and input ports. So some examples I have written here: AND gate, NAND and OR. So first one is AND gate, inputs are A and B and output is out. So here you can see the syntax and then instance name, which is G1 here, and then output out, comma A comma B. Similarly for NAND gate, you can write NAND G2 and then out, comma A comma B. So in this manner you can write the syntax. In this example, here you can see how we can write the Verilog code in gate level modeling. So in this figure you can see AND gate and XOR gates are there. So for this circuit, how should we write the Verilog code? Module and then module name. Then we have to specify all the input output ports, then all the input ports, all the output ports, and then for AND gate we have to write and then instance name, which is AND gate here, and then output O1, comma I1, comma I2. Similarly for XOR gate, it is XOR, then XOR gate, O2, comma I3, comma I4, and then end module. So in this manner we can write the Verilog code in gate level modeling. Another example is also here. So you can see without giving the instance name, also we can write this circuit. You can see OR gate is there, then AND plus NOT. So NAND gate is there, OR plus NOT, which is NOR gate, and XOR plus NOT, which is XNOR gate. For that, simply we have to write OR and then output and input ports. You can skip the instance name part. Now we have to study about the buff NOT gates, which is the second category of basic gates. It's one scalar input and one or more scalar outputs are there. Buffer and NOT gate, you can see the symbol, only a difference is the bubble. In NOT gate we have bubble, in buffer gate there is no bubble. Truth tables are there, in it the inverted output we will get. So here also I have considered 4 different values 0, 1, X and Z. In case of buffer, when input is 0, output is 0. When input is 1, output is 1. When input is unknown, then output is also unknown. And in case of high impedance, the output is unknown. Similarly, in case of NOT gate, when input is 0, then output is 1. When input is 1, then output is 0. For unknown, the output is also unknown. And for high impedance, the output is unknown. Now, in this example, you can see how we can write the Verilog code for buffer and NOT gates. Simply, you have to write the gate name, which is buff, and then the instance name, and then output and inputs. Similarly, for NOT gate also, NOT and then the instance name, and then output and input. So, in this manner, we can write the Verilog code for buff NOT gates. Now, we have to start the buff if not if gates. So these gates have an additional control signal. Actually, they propagate if the control signal is given. Otherwise, the output will be in high impedance state. 4 different types of buff if not if gates are there. Buff if 1, buff if 0, not if 1 and not if 0. So buff if 1 means buffer with active high control signal. And buff if 0 means buffer with active low control signal. So this buff if 1 or buff if 0 is nothing but buffer gate only with an additional control signal, and this control signal can be active high or active low. Similarly, in case of not if 1, it is a NOT gate with active high control signal, and not if 0 is a NOT gate with active low control signal. Here you can see the truth table for buff if 1, buff if 0 and not if 1, not if 0. I hope this is clear to you. And now in this example, you can see how can we write the Verilog code for this circuit. The first gate is a NOT gate with active high control signal. So this buff if 1, third one is buff if 0, and the last one is not if 0. So very simple code is there. First of all, the gate is buff if 1, and then buff gate 1, which is the instance name. You can give any name here, and then output and input ports. So similarly for not if 1, not if 0 and buff if 0, you can write the Verilog code. I hope the two categories, buff if, not if and basic gates, are now clear to you. If you have any doubt, you can ask. Now we have to talk about the gate delays. So in Verilog, we can introduce gate delays in the logic circuit. So three different types of delays are there: rise delay, fall delay and turn off delay. So starting from rise delay. So in rise delay, the gate output transits from 0, x or z to 1. Mean to say, whenever there is a transition from 0, x or z to 1, then this is called the rise delay. Actually, the time duration required for that transition is called the rise delay. Similarly, in case of fall delay, the transition is from 1, x or z to 0. So that duration is called the fall delay. Now, in case of turn off delay, whenever there is a transition in gate output to high impedance value from any other logic value. Mean to say, from any other logic value, that is 0, 1 and x, there is a transition to z value. That delay is called the turn off delay. One more thing guys, if the gate output transition is to a don't care value, then the minimum of the three delay will be considered. For example, if rise delay, fall delay and turn off delay, all these three values are given and the transition is to a don't care value, so in that condition we have to consider the minimum delay value. Here you can see the syntax. If a single delay value is given, then you have to consider that in your Verilog code. If rise delay and fall delay separate value is given, then you have to write both the values, and if rise delay, fall delay and turn off delay, all the values are given, then you have to consider all these values while writing the Verilog code. One more thing, if in the question no delay value is given, then by default you have to consider as a ideal circuit, you can say, or as an ideal gate you have to consider, but if delay value, to consider that value while writing the code. So in case of single delay value, first of all you have to write the gate name, then hash delay value and then instance name and then output and input ports. Similarly, if rise delay and fall delay both are given, then you have to write gate name, then hash rise value comma fall value, then instance name, and then all the values rise value, fall value and turn off values are given, then you have to write the gate name, hash and in comma turn off value, then instance name and then output and input ports. So I hope this syntax is clear to you. You can also understand this by this example. So here AND gate and OR gates are there. AND gate has a 5 time unit delay and OR gate has a 4 time unit delay. So in this Verilog code you can see I have written AND then hash 5 and then instance name, output and input. Similarly for OR gate it is OR then hash 4 instance name and then output and input. So in this manner you can insert the delay value while writing the Verilog code. Now we will consider some more examples, and as we all know, in case of half subtractor, 2 inputs are there and 2 outputs, borrow and difference are there. So difference is nothing but A XOR B if A and B are inputs, and borrow is A bar B. So here in this Verilog code you can see, first of all I have written module, then module name and then borrow difference A comma B. Then you have to specify input and output ports. Then I have taken wire W1. Actually this wire W1 I have taken to perform the negation of input A. So here you can see XOR, then the instance name x1 and then difference comma A comma B. This is for the XOR gate. Then for NOT gate I have written NOT n1 and then w1 comma of a, and then we will send that negated value from the borrow operation. So for AND gate, here the code is AND, then instance name, and then borrow comma w1 comma b, AND module. So this is the Verilog code for half subtractor circuit. One more example. Here in this circuit, AND or XOR gates are there. So you can see how can we write the Verilog code for this. You have to start from module. So module, then module name, output and input ports. Then you have to specify all the input and output ports. Here I have taken 3 wires, W1, W2 and W3. And then AND gate, instance name is A1. For XOR gate, instance name is X1, and OR gate and AND gate. So these are very simple example, and I hope today's video is clear to you. So starting from the continuous assignment. So actually the gate level modeling is the lowest level of abstraction. You can use this for small circuits, but when there is a complex circuit, in that situation you cannot use the gate level modeling because it will be very difficult for you when you are representing a complex, a large circuit in terms of logic gates. So it will be better if you are using data flow modeling. Mean to say, data flow modeling provides a powerful way to implement a design. So in data flow modeling, there is a continuous assignment, and continuous assignment is used to derive a value onto a net. In data type video, I have already explained that in a net data type, you cannot store a value. It is a continuously driven thing. As soon as there is a change in the input, it will reflect to the output net. So a continuous assignment replaces gates in a description of the circuit and describes the circuit at a higher level of abstraction. So in continuous assignment, we use the keyword assign. So talking about the characteristics, the left hand sides of an assignment must be a net data type, and the right hand side can be of reg or net type. Continuous assignment is always active, and delay values can be specified in that assignment in terms of time units. So in this example, you can see the out is net type variable and in1 and in2 are reg type variables. So simply by using assign statement, you can assign the value to out variable. Simply here I have written assign out equals to in1 and in2. Instead of this in1 and into expression, whatever value you want to assign to the left hand side variable, you can write here in the right hand side. So another example I have taken here, I have written assign, and then by using the concatenation operator, cout and sum. So here cout is a scalar net and sum is a vector net, and then I have assigned the value a plus b plus c in. So in this manner, you can use this assign statement. Now we will talk about the implicit continuous assignment. So in implicit continuous assignment, instead of declaring a net and then writing a continuous assignment on the net, Verilog provides a shortcut by which a continuous assignment can be placed on a net when it is declared. So mean to say, instead of writing 2 lines, first declaration and then assignment, you can perform both the tasks in a single line. You can see here in this example. In first example, it is the regular continuous assignment. First, I have declared the variable out as a wire type, and then I have assigned the value. Instead of that, by using implicit continuous assignment, you can directly declare a value and assign an expression to it in a single line only. So this is called the implicit continuous assignment. Also, there can be only one implicit declaration assignment per net. Why? Because a net is declared only once. So there should be only one implicit declaration assignment. I hope you got the meaning. Now we will talk about the delays. So delay values control the time between the change in a right hand side operand and when the new value is assigned to a left hand side. Mean to say, with the help of delays, we can control the timing. At what time we want to calculate the value of right hand side variable and at what time we want to assign the value to the left hand side variable. So basically there are three ways by which we can specify the delays in continuous assignment statement, and these are regular assignment delay, implicit continuous assignment delay, and net declaration delay. So starting from regular assignment delay. So here in regular assignment delay, after the keyword assign, you can specify the delay value. Here I have written has 10, I am taking 10 time units delay, and then I am assigning in1 and in2. This expression I am assigning to out variable. So as soon as there is a change in the right hand side variable, that value will be calculated, and the final value, that is the calculated value, will be assigned to the left hand side variable, which is out here, after the 10 time units delay. In this waveform, you can see at 20 time units, in1 and in2 signals are changing, and whatever we are getting after performing in1 and in2 operation, that value will be assigned to out after 10 time units delay. That is, at 30 time units, the value is assigned. So this is the meaning of the regular assignment delay. One more thing guys, an input pulse that is shorter than the delay of the assignment statement does not propagate to the output. Mean to say, here you can see in the in1, there is a change in the in1 from 80 to 85, but the width is 5, which is less than the time delay, which is 10. So that value will not be reflected in the out signal, and this is called the inertial delay. So in inertial delay, if there is a change in the input signal, but that change is for less than the delay time, then that value will not be reflected in the output signal, and that is called the inertial delay. Then we will see the implicit continuous assignment delay. So what is this delay? Implicit continuous assignment we have already seen. In single line, we can perform both the things, declaration and assignment. Here you can specify the delay values as well. In this example, you can see wire, and then I have written has 10, which is the delay here, and then I am assigning in1 and in2 to this left hand side variable out. So in this manner, you can specify the delay in implicit continuous assignment, and this delay is called implicit continuous assignment delay. I hope it is clear to you. Now we will discuss the net declaration delay. So a delay can be specified on a net when it is declared without putting a continuous assignment on the net. Mean to say, when we are declaring a net, at that time only we can specify the delay value, and that is called the net declaration delay. So here in this example, you can see I am declaring a net variable which is out, and while declaring it, I am specifying the delay value, which is 10 time unit here, and then I am assigning the value in1 and in2 to this out variable. So in this manner, you can assign this net declaration delay. So finally, we have completed today's topic, and now we will discuss few examples, and with the help of these examples, you can clear today's topic. So first example, I have taken 4-bit full adder. So as we all know, in 4-bit full adder, 3 inputs are there and 2 outputs, sum and carry, are there. So here in this Verilog code, first of all you have to write module, then module name, and then all the input output ports. After that you have to declare IO ports. Which ports are output and which ports are input, you have to declare that, and then you have to specify the function of full adder. So here I have written assign, and then by using concatenation operator cout comma sum, and then I am assigning the value a plus b plus c in. So in this manner you can write a Verilog code for a 4-bit full adder circuit. So here you can see guys, if you are using a data flow modeling, so your code will be very simple and very short. That's why it is preferred for any complex circuit. Here in this second example, I have taken a 2 to 4 line decoder. I have written a Verilog code by using data flow modeling. So in 2 to 4 line decoder, as we all know, 2 inputs are there and 4 output lines are there. So as we all know, in 2 to 4 line decoder, 2 input lines are there and 4 output lines are there. One enable signal is also there. It may be of active high or active low type. So A and B are two input lines and D is output line. This D is a 4-bit vector and E is the enable signal which is active low here. So here I have assigned the value to D of 0, D of 1, D of 2 and D of 3. So in this manner you can write the Verilog code by using data flow modeling. So two ways I have represented. In first one, I have written assign keyword for all the 4 lines. Instead of that, you can write single assign keyword and then you have to assign the values which are comma separated. So both the ways are correct. You can use any one. So start with structured procedure. So Verilog supports 2 structured procedure statement, always and initial. So all behavioral statements are written inside these blocks. These block runs in parallel manner, mean to say these blocks are nothing but concurrent in nature and their activity starts at 0 simulation time. One more thing, these blocks cannot be nested. Mean to say nesting is not allowed. Inside one always block there cannot be any other always block. Also inside one initial statement there cannot be any another initial statement. So start with initial statement. So this initial statement is once executable. Mean to say it will executed one time only and the execution starts at 0 simulation time. This execution stops when the last statement is executed. In case of multiple initial statement, parallel execution is there. Mean to say all initial statement will be executed parallelly. And if there are multiple statements inside an initial block, in that condition we need to use begin end state. So here you can see in this example I have written module, stimulus, then I have defined some variables. After that I have used multiple initial blocks inside this Verilog code. So in first initial block, since only one statement is there, so no need to use any begin end statement. But in second initial block, I have defined multiple statement. So in this condition, we need to use this begin end block also. Similarly, in third initial block also, I have used this begin end because multiple statements are there. And finally, in this initial statement, only one statement is defined, so no need to use begin end. So in this manner, you can use initial block in your Verilog code. And here is the simulation result, so you can check. Now, we will see the always statement. So this always statement repeats continuously throughout the simulation time duration. Since the initial block is concurrent in nature, this always statement is also starts at 0 simulation time, and in case of multiple always blocks, parallel execution is there. Mean to say if there are multiple always block, so all the always block will be executed parallelly. And there can be a deadlock condition also if there is no control for the simulation time. So we need to use this always statement wisely. We need to give some condition, we need to give some sensitivity list. So here is the example how you can use this always statement in your Verilog code. So here I have used both initial and always block in the Verilog code. So simply I have written always and then #10 clock equals to negation of clock. Since here I haven't defined any particular condition for this always, so this clock will be negated after all 10 time units until this $finish will occur. So in this manner we can use this always block in our Verilog code. Now we will start the procedural assignment. So procedural assignments update value of reg, integer, real or time variables. Mean to say once the variable values are updated, it will not be changed until and unless another procedural assignment updates the variable with different value. Also, these procedural assignments are different than the continuous assignment. So there are mainly two types of procedural assignment, blocking assignment and non-blocking assignment. So blocking assignment is represented by the sign equals to. These statements are executed sequentially. Mean to say, the statements will be executed in the order they are specified. One statement blocks the execution of another statement until it is executed. Mean to say, the next statement will be executed if the previous statement will
be executed completely. Then only the next execution will happen. Also, in case of blocking assignment, delays value will be added. And the reason is the execution happens in the given order. Mean to say, in whatever order we have defined this statement, in that order only the execution happens. So here the delays value will be added. Also, blocking assignment can be used in both procedural and continuous assignment. So here you can see the example. Inside this initial, I have used this begin end, and then multiple statements are defined here. So here I have used the blocking assignment. X, Y, Z, I am assigning some value. Then to count variable, I am assigning 0 value. Then this reg A, reg B value. And then after some time delay, I am assigning the value. So in this manner, you can use the blocking assignment. Now coming to the non-blocking assignment. So it is represented by sign less than equal to. These statements are executed concurrently. Mean to say, the right hand sides are evaluated first and then it is specified assignments are scheduled. These non-blocking assignment can't be used in continuous assignment statement or in a net declaration. Here you can see the example. Inside this initial block, I have used this begin end and then multiple statements are written. Here I have used both blocking and non-blocking assignment, but it is always recommended not to mix these blocking and non-blocking assignment. Always try to use one assignment at a time. So now we will talk about delays in procedural assignment. So guys, in data flow modeling video, I have talked about the delay values, but that delay values are specific for the continuous assignment. And now I am going to talk about the delays in procedural assignment. So don't mix these two types of delays and don't get confused. So for procedural assignment, two types of delays are there: regular delay and intra-assignment delay. So starting with the regular delay. So if delay value is specified, then at that time the entire statement is executed and assigned to the left hand side. Mean to say, this is the delay before the right hand side variable is evaluated and assigned to the left hand side. So the entire operation will be delayed in case of regular delay. So here you can see the example. Here in this initial block, I have written x equals to 0 without any time delay and then has 10 y equals to 1. So here this 1 value will be assigned to variable y after this 10 time units delay. So this is the meaning of the regular delay. Also in this line you can see, here I have written hash y x equals to x plus 1. So this x plus 1 value will be assigned to this x variable after y time units delay. So I hope this regular delay is now clear to you. Now we can see this intra-assignment delay. So intra-assignment delay is nothing but the right hand side of the equation is evaluated at current time, but the value is assigned to the left hand side variable after the delay time. This intra-assignment delay can be used in both blocking and non-blocking assignment. So here in this example, you can see in this line y equals to hash y x plus z. So this x plus z value will be evaluated at current simulation time, which is nothing but 0 time. And this x plus z value will be assigned to the left hand side variable y after 10 time units. So this is the meaning of intra-assignment delay. I hope it is clear to you. Now we can see the block statement. So two types of block statements are there: sequence block and parallel block. Sequence block are nothing but begin end block, which is used to group multiple statements. These statements are executed in order they are mentioned. Means in whatever order we have written the statements, in that order only the simulation will be happen, and the delay is treated relative to the simulation time and the previous statement. However, in case of fork join, it is used to group multiple statements, but the statements are executed in concurrent manner. And here the delay is treated relative to the simulation time of the entering the block. Mean to say, at what time we are entering to the block, that value will be considered for the delay. So here you can see the example for the sequence block. So here I have used begin end inside this initial block, and the blocking assignment I have used, this is without any delay time. In this initial block you can see I have given some delay time. So this x equals to 1 tick b0, this 0 value will be assigned to x variable at 0 time units. Then hash 5 y equals to 1 tick b1, so this 1 value will be assigned to variable y after 5 time units. Then hash 10 z equals to x comma y. Now since we have used this begin end, so the delay values will be added. So this execution will be happened at 5 time units. This simulation will be happened at 5 plus 10, that is at 15 time units. And this simulation will be happen at 5 plus 10 plus 20, that is at 35 time units. So this is the meaning of the sequence block begin end. Now you can see the parallel block, that is fork join. So inside that fork join, statements will be executed concurrently. Mean to say here the delay values will not be added. So the first statement will be executed at 0 time unit. This statement will be executed at 5 time units. This line will be executed at 10 time units, and finally this line will be executed at 20 time units. So here you can see inside this fork join the delay values will not be added. It is with respect to the simulation time when we are entering to the block. Now we will see the conditional statement if else. So here the keyword if else are used. It is the decision maker statement, and if we are using multiple statement inside this if else statement, then we need to enclose it with begin end block. Also we can use the nested if else if statement. So here we can see the syntax. So basically we have three different types. In type 1, we are only using this if. So if and then the expression. If the given expression is true, then the statement will be executed. In type 2, we are using both if and else. If, then the given expression. If this expression is true, then this statement will be executed. Otherwise, the given statement will be executed. This is the if else. And then we can use the nested if else if, which is nothing but if and then the given expression. If this expression is true, then this statement will be executed. Else if the next expression is true, then the next statement will be executed. Else if this expression is true, then this expression will be executed. And finally, else default statement. If all these expressions are not true, then finally this else value, that is this default statement, will be executed. So this is the meaning of if else conditional statement. Now we will talk about the multi-way branching, that is case statement. So sometimes we cannot use this if else statement for our Verilog code. So that time we can prefer the case statement. And if there are multiple statements, then we need to use the begin end block. So here you can see the syntax. I have written case and then the given expression, the expression on which we are applying the case statement. Then we have to write the different condition of this expression. First condition, second, third and fourth. Accordingly, whatever statement we want to execute, we have to write that. At last, we have to write the default expression. This is the default statement. If all these expressions are not true, then this default value, that is this default statement, will be executed, and then end case. So in this manner, we can use this case statement in our Verilog code. And now we will talk about the last topic of today's video, which is looping construct. So there are 4 types of looping statement in Verilog: for loop, while loop, repeat and forever. So these looping constructs are very similar to the C programming language. These looping statements are used inside an initial or always block, and these looping statements can have the delay values as well. So one by one we will understand. So starting from while loop. So in the while loop, the syntax is while and then in parenthesis we have to write the expression. So the meaning of while loop is that the while statement executes until the while expression is false, and multiple statements are grouped in begin end. This while loop is non-synthesizable in nature. So here in this example you can see I have written initial, then in begin end First of all, I am assigning this 0 to the count variable, and then while, and the expression is count is less than 128. After that, the statements are written. Since multiple statements are there, so I have used the begin end block. So the meaning of this while loop is that the given statements will be executed until this expression becomes false. Till then, the statements will be executed. So this is about the while loop. Now we will talk about the for loop. So generally, this for loop consists three parts: initialization, termination, and then increment or decrement. This for loop provides a more compact loop structure than while loop. So here in the syntax you can see for, and then first of all the initialization, then termination, and then increment or decrement. So here I am incrementing the value with 1, and then I have written the statement. So this is about the for loop. Now we will see the repeat loop. So this repeat loop iterates for a fixed number of times, and there will not be any expression required for this loop. Repeat loop must contain a number, and this number is equal to how many number of times we want to repeat the given expression. This is the meaning of repeat loop. So here in syntax you can see I have written initial. Inside this begin end block, I have written clock equals to 0 and then repeat 128, and then I have written the statements inside this begin end block. So the meaning of this repeat block is that this repeat loop will be executed 128 times and then it will be ended. So this is the repeat loop. And then the forever loop. So forever loop mean to say it executes forever until $finish or disable statement is encountered. Forever loop also does not require any expression. So here you can see the syntax. Inside this initial block I have written begin end and then clock equals to 1 tick B0 and then forever #10 clock equals to negation of clock. So forever this clock value will be negated after 10 time units until and unless any $finish or disable statement will be encountered. So this is the meaning of forever loop. So today's topic is now completed and we will see some examples so that today's video will be more clear to you. So the first example is 4x1 multiplexer. So here I have used the behavioral modeling to write the Verilog code for 4x1 mux, and I have used the case statement. So here you can see I have written module, then module name, and then input and output ports, then the port declaration. After that I have written this always statement. So always at, and then this is the sensitivity list. So here we have different ways to write the sensitivity list. Either we can write in this manner S1 or S0 or I0, or it can be comma separated as well. Mean to say we can write it as S1, comma S0, comma I0, comma I1 in this manner, or simply you can use one asterisk sign here. So by default it will consider all these variables. So we have different ways to write this. So inside this initial always block, in begin end I have written the case statement. So case and then S1 comma S0. So in these two variables I am applying the case statement. So the 2-bit values could be 00, 01, 10 or 11. On different condition, different statements will be executed. By default I have given the value out equals to 1 tick bx. Mean to say if the value of S1 S0 is 00, then I0 will be assigned to out. In case of 01, I1 value will be assigned to out. In case of 10, this out I2 value will be assigned to out. And in case of 11, this I3 value will be assigned to out. And by default, if all these conditions are not true, then the unknown value will be assigned to out. Then end case, end and end module. So in this manner, you can write the Verilog code for 4x1 multiplexer by using behavioral modeling. Another example, here I have written the Verilog code for 4-bit counter. So here you can see I have written module, then module name, input output ports, then the port declaration. After that, always at pause edge clear or neg edge clock. Now here the meaning is these clear and clock signals are not synchronized. If I am writing only always at pause edge clear or always at neg edge clock, at that time these two signals are synchronized. So here inside this begin end block, I have written if clear. So if this clear signal is high, then the 0 value will be assigned to Q. Else Q plus 1 modulo 16 will be assigned to Q. Now here I have used this modulo 16 because it is 4-bit counter. So it will count from 0 to 15. And after 15, it will again reach to 0. So that's why here we have used this modulo 16 operation. End and then end module. So in this manner, you can write the Verilog code for 4-bit counter. So our first topic is system task. So there are some task and function which is used to generate the input and output during the simulation, and it is represented by the $sign. So the first category is internal variable monitoring system task. In that we have $display, $monitor, $write, $strobe. So talking about the $display and $write, so both the system tasks are used to print the messages, but the difference is $display automatically adds a new line character to the end of its output. However, this $write don't add any new line character. Both $display and $write represents the current variable, current value of the variables. Talking about the $strobe, so it displays the simulation data at a selected time. That is at the end of the current simulation time, when all the simulation events that have occurred for the simulation time. And the $monitor is mainly used for the monitoring purpose. Each time a variable or an expression in the argument list changes the value, the entire argument list is displayed at the end of the time step. So for this purpose, we use the $monitor. Here you can see the syntax, all this $display, $write, $strobe, $monitor, same syntax is there. In this double quotes, you have to write the string format, and then after comma, you have to write the parameters which you want to print. So we can understand it with the help of example. So in this example, you can see I have taken this new reg variable, which is of reg type, and then in this initial block, first of all, I have given this value 1 tick b1 to this variable new reg, and then I have given the command $strobe, $display and $write, and this new reg value is also changed to 0. So here you can see the format. In double quotes, you have to write the string format, and then after comma, you have to write the parameter value which you want to display. So let's see the simulation result. So here we'll get for this strobe, the value is 0. Why? Because see, this $strobe is nothing but it displays the value at the end of the current simulation time. So this new reg value, earlier it is 1, but finally its value is changed to 0. So this $strobe represents the final value, which is 0. Then this $display represents the current value only. So in this $display, you will get this value 1 because it represents this current value, not the final value. And this $monitor, since whenever there is any change in the value of variable, it will print that value. So earlier it was 1 and then it is changed to 0. So both the values will be printed in this $monitor command. So here you can see first it was 1 and then it is changed to 0. So in this manner, you can use $strobe, $display, $monitor and $write in your Verilog code while writing this test bench. Here you can see the $random. So $random provides a mechanism for generating the random numbers. It returns a new 32-bit random numbers each time it is called. So the random number is a signed integer. It can be positive or negative. Seed parameter controls the number that $random returns. So it is mainly used for the stimulus. Then see the second category, which is simulation control task. So here we have $reset, $stop and $finish. $reset is used to reset the simulation process. That is, it returns the simulation back to 0 time. $stop is used to suspend the simulation, and $finish is used to terminate the simulation. So what is the difference between this $stop and $finish? $stop suspends the simulation. Mean to say you can again start your simulation after some time, but this $finish terminates the simulation. Mean to say you cannot resume your simulation once you will give that $finish. So this is the basic difference. Now we will talk about the third category, which is simulation time related task. Here we have $time, $S time and $real time. So this $time represents the current simulation time as a 64-bit integer. $S time returns current simulation time as a 32-bit integer, and this $real time returns the current simulation time as a real number. So you can understand these things with the help of this example. So here you can see I have taken two examples. In this example, in this initial block, I have given a value with this time delay 1.55, a equals to 0, then again hash 1.55, a equals to 1, and then at hash 50 $stop I am giving this. In this always block I have given hash 50 clock equals to negation of clock. So the initial value of clock was 0, and then we are changing this value. Don't worry about this tick time scale. It is a compiler directive. This 10 nanosecond is the time unit, and this 1 nanosecond is the time precision. And just forget about this logic. This is nothing but a data type in system Verilog. And here in this initial block, I have taken this $monitor. So here I want to print this time value. For this, I have taken $time, then clock, and then a value. So let's see the simulation result. So first of all, this time was 0, clock was 0, and the initial value of variable a was unknown. Then it was 1.55, but we are giving this $time. So $time will consider the integer value only. It will not consider any real number. So this 1.55 will be considered as 2. So this 2 into time unit 10. So it will be 20 nanosecond. So at time 20, the clock value will be 0 only, and the variable a will be 0. Then at time 30, 30 is what? 1.55 plus 1.55. So it will consider as 30. So this 3 into 10, that will be 30. So at 30, clock will be 0, a will be 1. And finally, after 50, we are just stopping. We are giving this $stop command, but at hash 50, we are just negating the clock value. So here you can see at time 500, we are getting clock equals to 1 because clock has negated at 50 time unit delay, and a value is 1. So here in the second example, you can see only the difference is here I have taken $real time instead of $time. So the difference will be in the simulation result. It will consider these real time values. So initially time was 0, clock was 0, and a was unknown. Then this 1.55 will be considered as 1.6 because the precision was 1 nanosecond only. So 1.6 into this 10 time unit. So it will be 16 only. So at time equals to 16, clock is 0, a is 0. Then 1.55 plus 1.55, so it will be considered as 3.2. So 3.2 into 10, so it will be 32. So at time equals to 32, clock was 0, a equals to 1. Here we have given 1. And then at 50, it will be 50 into 10, which is 500. Clock has negated, and a value is 1. So in this manner, you can use $monitor, $stop, $time, $real time, tick time scale, compiler directive while writing the test benches. Now we will talk about the compiler directive. So a compiler directive may be used to control the compilation of the Verilog description. We use this tick mark whenever we use the compiler directive. So in this video, we mainly discuss these three compiler directives: tick define, tick include, and tick time scale. So talking about this tick define, it creates a macro for the next substitution. It can be used both inside and outside the module definition, and can be used in the source description by using this tick character and followed by the macro name. So here you can see in this example, tick define size 8. So this size is macro, and here I am giving the value, and then while writing the code I am using this macro only, tick size. I am not using this value of this size. So the benefit of using the tick define is that you can change your Verilog code just by changing this single line. Whenever you want to change the value of this size macro, just you need to change this one. Instead of 8, you can write 16, 32 or 48, and rest of the code will be in terms of this size macro only. So you need to change only single line and your entire code will be changed. So this is the benefit of using tick define. Now we will talk about the tick include. So this tick include is used to insert the entire content of a source file to another file during the compilation. It is used to include global or commonly used definitions and tasks. So here you can see, you can write this tick include and then in double quotes the name of the file from which you want to just insert the content. You have to write the name of that file here. So in this manner you can use tick include compiler directive in your Verilog code. At last we will talk about this tick time scale. As you have already seen in the previous example, we have used this tick time scale to define the time precision and the time unit. So in this manner you can define tick time scale and then this is the time unit / time precision. So whenever you are writing a test bench, you should define this tick time scale compiler directive. Otherwise, the default value will be considered. So Verilog provides tasks and functions to break up large behavioral designs into smaller pieces. Task and functions allows the designer to abstract Verilog code that is used at many places in the design. So basically it provides the reusability. Tasks and functions are like subroutines. We can define a particular functionality using either functions or call, and then we can call these functionalities from anywhere, anytime. So it is something like subroutine, and we need not to write the code again and again. If we perform a particular operation, we can define a task or function for that, and whenever we need that operation, we just call that function or that task. This is the advantage of using task and functions. And these tasks and functions are very important part of Verilog code. And if you are just learning Verilog and if you are just practicing writing the codes, then try to use this task and functions in your code. That will increase the readability of your code, and your code will be reusable also. It looks very clean, because again and again you are not writing the same thing, you are just calling. So it will increase the readability, and yes, your code will look more clean. So first we will see the task. What is task? Let's see. So the tasks are declared with the keyword task and end task, and task can enable other tasks and functions. It may execute in non-zero simulation time, and it includes delay, timing or timing control statements. Task may also have 0 or more arguments of type input, output or in-out. Also, this task do not returns any value, but it can pass multiple values through output and in-out arguments. So here you can see the syntax and examples. So the syntax is very simple. You can see I have written here task, and then the name of that task you have to write, whatever name you have to give in, you can write here. Then all the input, output and in-out port list you have to write, and then inside this begin end block you have to write the statements and then the end task. So this is the simple syntax of the task. Now we will see some examples. So here I have taken the task sum. So sum is the name of this task sum, and then you have to write the input and output ports. A and B are 8 bits input and C is a 8-bit output. Then inside this begin end block, I have written C equals to A plus B and then end task. So in this manner you can write your task, and if you have to just call that task, so how you can call that? Here is the way how you can call it. So initial, and inside this begin end block I have written reg and then 8-bit variables x, y, z, and then I have called that sum task, sum and then the arguments x, y, z. So here these arguments x, y, z will be considered in the same order of that a, b, c. So x and y will nothing but a and b, and z will be c. So here you will get z equals to x plus y. So in this manner you can write a task and then you can call it by giving different arguments. We will see some more examples. So first example, here I have taken a simple task, and here I have written module, then simple task, then task convert. So this convert is a name of that task, and the simple task is the module name here. So convert is the task name, and then I have written here input and output ports. So temp in is the 8-bit input and temp out is the 8-bit output, and then inside this begin end I have written the statement temp out, and then whatever value we have to give to this, temp out, I have written this, and then the end task. So in this manner you can define your task. Also you can write your task using global variables. So what is this global variable? Actually, while writing the task, if you are defining the variable inside that task, then that is known as the local variables, and those variables are limited to that task only. You cannot use those local variables outside the task, but you can derive the global variables inside the task, and global variables are nothing but the variables which you are defining outside the task. So here you can see I have defined two variables, temp in and temp out.
Since these variables are defined outside the task, so it will be considered as global variables. And you can use these global variables inside your task. So inside this task, I have written inside this begin end block temp out and then 9/5 into temp in plus 32. So in this manner, you can use global variables in your task. And here you can see how you can call a task after writing. So simple code I have written here, module and then task calling. This is the module name. And then I have written all the ports, temp A, temp B, temp C and temp D. I have just defined the ports, input ports and output ports. And then I have included one file which is mytask.v. This is a file where I have defined the task. This is the file name. And then here I have taken two always block. In one always block, I have given temp A in sensitivity list, and in another always, I have given temp C in the sensitivity list, and then I have called the convert task. So here you can see convert and then temp A comma temp B. So this temp A will act as an input and this temp B will act as an output. Also here this temp C will act as an input and this temp D will act as an output. Actually, these arguments depends on the format of your task, how you have written there all the variables, all those ports. These arguments depends on that. So in this manner, you can call your task. So I hope task is now clear to you. I have few more points to tell about the task. Task can use both blocking and non-blocking assignments, and task can be disabled using a disable keyword. There are keywords enable and disable, so you can disable a task by using these keywords. We will see these things in more detail in our practice set. When I'll give some different codes, that time these things will be more clear. Also, task may have 0 or many arguments and doesn't return any value. As I have already told, task never returns any value. Function returns a value. So now we will see functions. What is function? Functions are declared with the keyword function and end function. Functions can enable other functions but not other tasks. Functions always execute in zero simulation time. Mean to say, we cannot include delay, timing or timing control statement inside a function. Sometimes a question is asked like find the error, and they just write a function, and inside that function somewhere they have just defined a time delay. So whenever you see a time delay or any timing control statement inside a function, that means there is an error, because we cannot define any delay value or any timing control statement inside the function. So these small question will ask in your exam or in your interviews, find the error kind of things. So also function must have at least one input argument and it returns a single value. They cannot have output or in-out arguments. So these are few of the things about the functions. Now we will see the syntax of the function. It is very simple. Function and then automatic, return type, then the name and then the port list. Here automatic is the optional thing. If you are writing the automatic function, that time you need to write this keyword. Otherwise, if it is static function, no need to write this keyword. Simply write function and then the name of your function and then the port list. Inside the begin end block, you can write your statements and then the end function. This is the simple syntax. Here I have given this example. I have written function and then 7 down to 0 sum. This 7 down to 0, that is 8 bits, are nothing but the width of this sum. And then I have taken input 7 down to 0 a comma b. Here I have taken two inputs and then inside this begin end sum equals to a plus b. So this function is giving a return value a plus b. So if we are passing two values a and b inside this function sum, so finally it will return a sum of these two values. And then end function. So this is the meaning of function. It will return at least a value. That means not at least. It returns single value only. This is the concept of function. Here we will see some more examples. First, I have taken a simple function. So here I have written module and then the simple function. Then function and the name of the function, which is my function. Then input a, b, c, d. Inside this begin end block, I have written my function and then a plus b plus c minus d. Whatever value you want to give to this my function, you can write here, and then the end function. So in this manner, you can define your function. And now it's time to call this function. How you can call this? Let's see here. Module and then the function calling. This is the module name and these are the arguments. Here I have taken input A, B, C, D, E and then the output F. I'm including this file myfunction.v. Actually, this myfunction.v file is nothing but the file where I have written the function which I'm going to call. That file you need to include. And here I'm writing assign f and then my function. My function is nothing but the name of this function and you are calling that function here. So my function and then the arguments a, b, c, d and whatever you want to just assign you can write here and then the end module. So in this manner you can define your function and you can call your function. I hope it is clear to you. Now we will talk about the difference between the task and functions. Task can call any number of functions or tasks within itself, but in case of functions, it can call any number of functions only, not any task. So task can call both function and task, but functions can call other functions only, not other tasks. Task cannot return any value when it is called. Instead, the task can have output arguments. However, in case of function, it returns a single value. When it is called, in system Verilog, the return value can be optionally voided. Actually, in system Verilog, we can use automatic task and functions, and that time it provides some functionality and some flexibility. So we will discuss those things in system Verilog videos. So these are the difference between the task and function. Also, task and functions both are synthesizable constructs. Functions are mainly used in combinational logic. However, the task can be used in both synchronous and combinational logic. Here I have given a difference between the automatic, that is reentrant task, and the static task. This automatic task is a part of system Verilog. We mostly use there only, but here for your knowledge I have just given this difference. So whenever you see this keyword automatic, don't be confused. You can use automatic task or automatic functions. It will just provide some flexibilities. In case of automatic task, there is dynamic allocation of memory. However, in case of static task, there is static allocation. So these are few differences between the automatic task and static task. We will discuss in detail in system Verilog videos. So first of all, I have written here two different formats. Yes, two formats, one for the combinational circuit and one for the sequential circuit. So this is the first format. Whenever you have a very simple Verilog code for any combinational circuit, then you should follow this pattern. Actually, this pattern is very much simple, and if you are using this pattern while writing the test bench, then you will not skip any command like initialization or the variation or that $monitor or $finish. So you will not be confused that time which thing you should write first and which command you should use. So that's why I'm suggesting you to follow this pattern, because I personally follow these patterns always. Always I follow these patterns, and you should also follow, because once you started following these things, you will feel very confident, very much confident, I'm sure. The benefit of using these formats are your code will look very neat and clean. Commands will not be skipped that time while writing the test bench. And so first we will see this first format. So here module and then test bench name, whatever name you have to give, you can give there. And then input declaration, output declaration, then duty instantiation. After that you have to use three initial blocks, first, second and third. In first initial block, you have to initialize your variables. In second initial block, you have to vary those variables. You can give a fixed value, some set of values you can provide to input variables, or you can use some loops here, for loop or repeat. These types of loop you can use. And then in third initial block, you have to use $monitor and $finish command. Along with that, if you are using EDA playground, then $dump files and $dump vars. These two commands you can use here in the third initial block. So you can see if you are following this pattern, then nothing will be skipped and you are writing in a very proper format. First initialization, then variation, then you have to monitor all those values. If you are writing test bench for a sequential circuit, then clock generation part should be there. So take one more initial block for clock generation. So this format is for sequential circuit test bench. So module, then test name. After that, input declaration, output declaration, duty instantiation. After that, take first initial block for clock generation,
second initial block for initialization, third initial block for variation of the input variables, and then in last initial block you have to give $monitor, $finish. In case of video playground, you can give $dump files and $dump vares, and then end module. So I hope these two formats are now clear to you, and we will see some examples in today's video, and through those examples I will explain how you can write the test benches. So this is the first example. I have taken full adder Verilog code. This code is very simple, and I hope this code is clear to all the students, so I'm not going to explain this. So simply here I have taken sum and carry two outputs and A, B, C in three inputs. Sum, the value is assigned A XOR B XOR C in, and to carry we are assigning A and B, B and C, C and A. So now we will see how we can write the test bench. So there are two different ways by which we can write the test bench for full adder circuit. First one is you can give some set of values to the input variables, and then you can check whether your circuit is working properly or not. Actually, the thing is, what is the need of writing the test bench? Why one should write the test bench? Just to test whether your design is working correctly or not. Through the test bench, you can check whatever design you are written, whatever code you have written, that is working correctly or not. So basically it is used to test your design. So we need to give different input values and whatever output is generated, by which we can check whether the circuit is working correctly or not. So here simply I have written module and then the test name, then reg type input, wire type output. Then it is duty instantiation. Here make sure this order should be same as that of the code. So here I have given this order sum carry A, B, C in. So while instantiating that, you need to give the same order. Then in first initial block I have initialized all the variables. In second initial block I have given some set of values A1, B0, C in 0, then A1, B1, C in 0. Like that only I have given some set of values with time delays. And then in third initial block I have given $monitor and $finish. Now again, $monitor I have explained in very much detail in compiler directive video. So if you have not watched that video, then please watch that and clear the concept of compiler directives, because those compiler directives are used in test benches. So here in $monitor, first we have written this $time. Try to use this $time because whenever you will check your terminal, so in case of this $time, you will get at what simulation time you are getting what output. So try to use this $time. Then here we have given the values A, B, C in, then sum carry, and here we have given %B because we need to print the values in binary format, and then $finish, end module. So in this manner we can write the test bench for the full adder circuit. This is the first way. Another way is that you can use the loop instead of giving some set of values. So again same thing, module, then test name, and then reg type input, wire type output. Only the difference is here we have taken integer I. Why this integer? Just for this for loop. That's why we have taken that integer. Then here we have done the instantiation part. Then in first initial block initialization is done. In second initial block we have applied a for loop. So in this for loop I is varying from 1 to 8 and it is incremented. It is less than 8 actually, so 1 to 7 it will vary, and then it will be incremented by 1. Then this I value will be assigned to A, B and C in, and after each value we have given this 10 time unit delay. And then in third initial block we have given $monitor and $finish. So this is the another way by which you can write the test bench for full adder circuit. I hope both the ways are now clear to you, and it's better to use loops instead of giving some set of values to the input variables. Then the second example is JK flip-flop Verilog code. Most of the students were asking how we can write the test bench or how we can write the Verilog code for JK flip-flop and some flip-flop conversion questions. So that's why I have taken this example. So here I have written module and then JK flip-flop. This is the module name, and then Q, QB, J, K and clock. Then input is J, K, clock, and reg type output Q and another output QB. Then I have taken some parameters: hold, reset, set, and toggle. For hold it is 00011011. Without parameter also you can write the code. It is completely your choice. Then assign QB equals to negation of Q. Then in this always block, always at pause H clock, we have applied case statement. Case J comma K. Now we are applying the case statement in this J and K variable. So in case of hold, we have to assign Q to the output Q. In case of reset, we have to assign 0 to this Q. Now hold means what? JK value should be 0, 0. In case of reset, JK value is 0, 1. In case of set, it is 1, 0. And in case of toggle, it is 1, 1. So in case of toggle, we are assigning negation of Q to that output Q. And then end case and module. So in this manner, you can write the Verilog code for the JK flip-flop. Now we can see how this test bench could be written for the JK flip-flop. So module and then JK flip-flop TB, reg type input we have taken, wire type output, then the DUT instantiation. After that, JK flip-flop is a sequential circuit, so we need to generate clock. So here in this first initial block, I have generated the clock. Now what is the way how you can generate the clock? So first you need to give some value. So clock equals to 1 tick B0. Initial value we have given 0. Then forever #5 clock equals to negation of clock. So after each 5 time units, this clock will be negated. It will be toggled. So here we have generated the clock. Then now in second initial block, I have initialized the value. So J and K, I have given 0, 0 to both the variables. And then in third initial block, I have given some set of values with time delay 10 time unit. And then in third initial block, I have given $monitor and $finish command. One more thing guys, what value you are giving here in $finish, that you have to make sure it should not be less than the time delay which you are providing here. It should be actually more than all the delay values you have given in the third initial block, because if you have given suppose 60 or 70 time unit delay here, total delay I am talking about, and here you have written #50. So all set of values will not be applied in that condition, and before that your simulation will be finished. So make sure this delay for the $finish command, it should not be less than these time delays. Then it is the terminal output. So you can check from here whether we are getting correct output or not. And don't be confused with these terminal outputs. I am giving just for the understanding purpose. Now it is your task to write the code and test bench by your own, and then test whether you are getting correct output or not. This is the third example, which is 4-bit synchronous loadable binary up-down counter. So most of the students have doubt how they can write the Verilog code for the counter circuit, because we have different categories in counters: up counter, down counter, up down counter, then loadable counter, synchronous counter, asynchronous counter. Different categories are there. So that's why I have chosen this example. Actually, I am trying to cover most of the topics through these examples, so that students can clear their doubt. Whatever small doubts they have, they can clear through these examples. So here I have written module, then the module name, here port declaration part, and then DIN, which is 4-bit input. Then other inputs are clock, reset, load, and up down. And then reg type count output I have taken, which is of 4 bits. Then in always at pause H clock, different conditions are there. What happened if reset is high? What happened if load signal is high? What happened if this up down is high? And what happened if it is low? So all the scenarios we have to cover. So it's better to use if else statement here. So here I have written if reset. If reset signal is high, then we need to assign 0 to this count. Else if load. If load signal is high, so that time this DIN value will be loaded to this output count. If this up down signal is high, so it will perform up counting, and if it is low, then it will perform the down counting. So here I have written if up down, then count equals to count plus 1, else it is count equals to count minus 1, and then end module. So in this manner you can write the Verilog code for up down counter. Now we can see the test bench here. So simply reg type input, wire type output, instantiation. Then in first initial block, clock generation part is there. In second initial block, I have given some values here. This is basically for the initialization. Then in third initial block, I have given different set of values to reset, load and up down, and this input D in. And then in last initial block, $monitor and $finish. One more thing I want to just make it clear. Whenever you are writing a test bench, try to cover all the functionality of your Verilog code. In advanced Verilog, we have a topic called code coverage. So in that, what we have to check whether the test bench is covering all the functionality of the code or not. How much coverage it is providing, and the meaning is that only. How much part is covered in that. So whatever functionality is there in your code, in your circuit, all those things should be covered in the test bench. So here it is reset, then load, then high value of up down and low value of up down. So we need to write a test bench which can cover all these scenarios. So that should be a perfect way of writing the test bench. So here I have given the terminal output. So you can see, first of all, we just make this reset signal high. So the output will be 0 that time because the circuit will be reset at that time. Then I have given load equals to high. So if load is high, so earlier the value was 0, and after giving this load signal high, the input, this D in input is loaded. So here the count value becomes 4. After that, this reset is 0, load is 0, and we have given this up down signal. So if this up down signal is high, that time this counter will perform up counting operation. So you can see here the count is incremented, 4, 5, 6, 7. These values are incrementing. And if up down is low, that time the counter performs down counting. So here values are decrementing from 10 to 9, 8, 7, like that the values are decrementing. So here you can see I have covered all the aspect: up counting, down counting, reset and load. And in that manner only you need to write a Verilog code test bench. Now this is the last example of today's video, which is a D flip-flop Verilog code. So this code is very simple. We have taken input D clock reset and reg type output Q and another output QB. We are assigning this QB with value negation of Q. Then in always at posage clock, if reset signal is high, then we are assigning 0 to this Q, else input D to this Q. So this is a very simple code of D flip-flop. Now we will see the test bench writing. The special thing is that here I have used task while writing the test bench. So whenever there is a complex design or a bigger circuit, that time it's better to use task while writing the test bench. It will give very kind of clean look to your code. It will be very manageable, and you will not be confused which thing you have to write first, what is second. You need not to be confused there. The simple way is that use task while writing the test bench. So here I have written module, then module name, reg type input, wire type output, and then instantiation. After that, in first initial block, we have generated clock. Then I have defined a task here. The name of this task is initialize. So this is the format of writing the task. So task, then task name, then in begin end, I have given two values, D equals to 0, reset equals to 0. So this is my task to initialize. That means it is performing initialize operation. Then I have written another task named stimulus. And here I have given two parameters I and J here. So whenever you are calling the task, you can give argument here. Okay, so here this I value is assigning to D and J value is assigning to reset. And then in third initial block, we are simply calling all the tasks which we have defined. So first, this initialize, what this task will do, it will initialize the variables. Then stimulus, I am calling this stimulus with argument 1, 1, then with 1, 0, then 0, 0 and 1, 0. So in this manner, you can give different arguments to this task stimulus. And then in last initial block, $monitor and $finish end module. And this is the terminal output. You can check whether you are getting correct output or not. So I hope today's video is clear to all the students. If you have any doubt, you can tell me in the comment section. And I hope you will follow those two formats of writing the test bench, one for the combinational circuit and one for the sequential circuit. Those formats are very useful if you are a beginner, if you are just starting learning a Verilog code, then it is recommended to use these formats. It's not a hard and fast rule to use that format only, but it will help you a lot. You will not getting confused while writing the test bench. Things will be very much clear. If any other guy is reading your code, that time also your code will be very clear, very much understand. If you have not joined our Telegram group till now, then join that group. And if you have liked today's video, then like the video, subscribe the channel and share the videos as much as possible. So thanks for watching.